All right, welcome. My name is Michael Caisse. I work with Kira Consulting. We are a small consulting group, about 10 people. It's our 11th year in operation. We deal with a variety of solving problems for people, full stack software from MCU all the way up to large distributed systems with 60,000 devices scattered throughout the US, checking in every 3 minutes to a 100-core cloud server. And we deal with software all the way in between, from very low-level things, you may have heard me talk about that type of stuff, C++ on MCUs, to very large things. We use Asio a lot for our communications, and that's what I want to talk about today. And I want to talk about it maybe from a slightly different point of view than you may have heard before. We're going to have code, but part of the problem with Asio is trying to just get a mental model of how the system works. And we'll try to establish that first. Having a good worldview of things helps us to place our problem that we're trying to solve into some domain where we can poke at it and get an idea of what it's going to do. And so it's good to have a good worldview. One nice thing, if you learn about Boost.Asio, you're learning basically about the TS for networking that has gone out for balloting. So you're learning the standard, or what's close to the standard C++ networking. So it's kind of like a double bonus, right? So let's start with taking a look at what Asynchronous I/O is, or what the library provides. It was originally written as a networking library. However, it provides a lot of different services. You can have serial ports and timers, file descriptors. You can write your own services, so that it's extensible. We use it for everything from CAN bus communication to weird communications on specialty hardware that we do. So it's easy to plug into the model and write your own types of services in order to handle the things that you want to handle, and then in an asynchronous, efficient manner. It uses a proactor. So you may be familiar with reactor-type patterns. The proactor pattern is a little bit different, and often is what causes the confusion. It's very scalable, and it has this portable abstraction layer. So a lot of people's introduction to Asio is the fact that you need to write networking code for both Windows and a Linux system and a Mac OS system. And so that portability provides something that we're all looking for. So what is asynchronous I/O? All right, so I have 3 daughters. I wrote this slide 6 years ago, actually. So they were younger back then. But I would say to daughter number 1, please make me a coffee. And I actually have really good kids. Her response is, sure, Dad. And off she would go to the coffee machine, and I would continue working along. And then all of a sudden, she would arrive at my desk with a cappuccino and say, here you go. And I'd say, thank you. Okay, that was an asynchronous transaction. I asked for a coffee. I don't know what's happening, but somehow she runs off to the kitchen where the machine is. I continue to work at my desk, and a coffee arrives, right? Nice asynchronous transaction. Daughter number 3 at the time, very enthusiastic about making coffees, loves to make coffees. In fact, she would usually ask me, can I make you a coffee, Dad? Sure. We would both go to the kitchen, and I would supervise the process and just kind of stand there and watch, right, as she makes the coffee. And then we'd both walk back to the desk, and then she'd hand me my coffee. Not an asynchronous transaction. However, that's how we do I/O a lot. We sit around and we wait for the process to finish, and then we get the result and we do something with it. All right, we don't want this. We want to actually be doing something at the same time that we've requested the I/O. So in more nerdy terms, right, we have a completion handler, done reading. We have this read file. We maybe give it a file name and a buffer where to put the data. And hey, let me know when you're done by calling some callback handler. That would be the done reading. So why do we want to do asynchronous I/O? What's the point? If you started off with this, you might naively write a client and a server, and the client connects and you have some connection that comes in to the server, and you write the server so that there's a read thread and a write thread. Some companies I've seen a read thread, a write thread, and a management thread. I have no idea what that is, by the way. Anyhow, so we've got like the read thread and the write thread. Well, that might be okay for your one client that connects, but as soon as those clients start increasing and you have more and more clients, you're utilizing resources that are doing nothing, right? You have threads that you have created, yet most of the time they're sitting around doing nothing except for consuming resources. What a waste. So we don't really want this. Most of the time, our clients can actually be satisfied by a single reader and a writer. So we have maybe a read thread and a write thread, or maybe one thread for reading and writing. That would even be better. So we want to be able to get to some asynchronous I/O model in which we are being notified when there's something to do. And at that point, we can then perform that action. All right, so this is story time. This is where we would like dim the lights. Because part of understanding how pro-actors work is understanding that worldview I was talking about. So are you ready? A pro-actor's story, or purple slushies, butlers, and brain freeze. Mom, Dad, Johnny, and Butler go to the beach. Dad tells Butler to wait at the slushy shack. After some time, Dad and Johnny go to get a slushie. Dad brings his own cup. He is greeted by the owner. I would like to order a slushie. Here is my cup. Please deliver it to Johnny when it is ready. Dad heads off to explore the beach. Johnny builds a sandcastle. Owner begins to make the slushie, and Butler waits. Owner starts the blender and goes back to take the next customer's order. Time passes. Ding! The slushie is ready, and owner moves the cup to the completion table where assistant is waiting. The assistant gives the slushie to Butler for delivery to Johnny. Butler is happy to have something to do. Butler delivers the slushie to Johnny, who is happy too. Butler returns to the slushie shack and waits. Sometimes, Dad will order multiple slushies, one for Mom and one for Johnny. That isn't a problem. Assistant just gives the first one ready to Butler. Butler can only deliver one at a time and returns for the second slushie. Other families come to the beach and bring their butlers, who also wait in the slushie completion line. This works well because it helps keep assistant's slushie completion table empty. Assistant still remembers that fateful day when no butlers came to the beach. There was also the time that each kid brought a butler. Disaster. No room at the slushie shack. Too busy, yet nothing was getting done. The families agreed that 2 butlers would be plenty for all. Now they share. Occasionally, tragedy strikes. Johnny will leave to chase waves without getting his slushie. Butler will die of exhaustion trying to find him. Or somebody will take their cup and go home while the slushie is being made. Then it gets poured on the floor. Yuck! Dad is sometimes very generous. Johnny would like 1 orange and 1 purple slushie. If both slushies are done at the same time and both butlers are available, then Johnny gets 2 slushies at once. This confuses Johnny and causes brain freeze. Susie is smarter and doesn't mind both slushies at one time. But most often, The dads are making requests to the owner. The assistant is monitoring the table. The kids are building sandcastles, and the butlers are waiting. All right, we have some credits to this story. Playing the role of initiator is dad. The asynchronous operation processor is the owner. The proactor is the butler. Asynchronous operations are the blender making slushies. The completion event queue is the completion table in our story. And the asynchronous event demultiplexer is the assistant. And then the completion handler was played by Johnny. We also had one called Susie. So personally, I need to create worldviews of how things are going to happen inside of different complex processes. And for me, having ideas like this work well. You might not like this, and you might want the more boring version. We'll get to that in a moment. But we also had additional roles. The operating system, what's played by the blender. The memory to be filled by the cup was an empty cup, and data in memory was a full cup. This is the boring version that we would normally show of this same diagram. You can find it online. So the lessons that we learn from this story are the lessons that help guide us on how a proactor is going to work and things that we should and should not do with it. First, all threads of activity that are in the slushy shack stay in the slushy shack. There were things happening in there. The owner was making stuff. There were things that were going on. The assistant was moving around. But we're not exposed to that on the outside. They stay within the shack. The butler delivered the results to the completion handler. So our interaction was through this butler. And the butler, which is really the handler thread, it was supplied by the family or the application. The application provides the thread that will be interacted with. We don't have to worry about some other strange thread interacting with us. The cup, which is memory, it was supplied and it's owned by the family or the application. The application owns that. By the way, that's one of the major differences between a reactor and a proactor. In a proactor, the application owns the spot where the memory is going to be filled up or delivered. The reactor, it's giving you buffers. Okay, so there are some other lessons. Not all handlers, Johnny in particular, liked having multiple results delivered at the same time. So we have things that sometimes are not multi-thread safe. Some handlers, Susie on the other hand, didn't care if they had multiple results delivered at one time. Don't leave the beach or the scope when a slushie is being made for you. It's kind of bad. So you've got a thread, it's looking for the completion handler to call, but the completion handler has gone out of scope. Not a great idea. A few handlers, threads, butlers, they can service many completion handlers. Most of the time in an asynchronous situation, we are waiting around for something to happen, events to occur. There's no reason to have a lot of threads to deliver that. All right, let's talk a little bit about Asio. And the easiest way to start approaching this is to just look at timers. And we can see how timers will interact and how they work. And then from there, we can build on this and do a little bit of networking in a moment. So the first thing we're going to do is we are going to get our I/O service. Our I/O service is the thing we're going to interact with. We're going to kind of think about that maybe mentally as our slushy shack. It's the thing where we're going to provide butlers to. It's the thing that we're going to get asynchronous requests into. And so we have our service. From there, let's create a timer. This is a deadline timer. The first thing that the deadline timer is going to want, in fact, almost anything that deals with the service is going to want, is which service it's associated with. So we pass the service as the first argument. The second argument is going to be the expiration for this deadline timer. We've picked 5 seconds. So the timer is associated with the particular service, and in 5 seconds is how it will, 5 seconds is the time that the deadline timer would go off. We begin the process by calling async wait. So async wait is going to be a non-blocking call. It starts the timer process. And there is one thing that we need to provide to it, which is the completion handler to call when all of this is done. That's like Johnny, right? And so we're going to use a Lambda function. We're simply going to print out what the time is right now and that the timer expired when the timer expires. We're going to print out some more information so that we know where we are, and then we're going to call service run. Service run is equivalent to that butler being supplied to the slushy shack that's going to handle the completion queue. It is the thread that is going to handle the callbacks for the completion handlers. Every time you call service run, that's providing one more thread to take care of completion events. And so at this point, we have one. It's the main thread, but we have one. And it's going to block. It's going to stay there until all work is done. So what happens when we do this? We get calling IO service run. 5 seconds later, we can see that our timer has expired and then done. So not too surprising. All right, let's do this. It's the same. We have an IO service starting things off. And let's create 2 deadline timers. So they're both going to go off in 5 seconds, timer 1 and timer 2. And we're going to go ahead and call something called timer expired, where we pass the ID, in this case timer 1, or the ID of timer 2, so we know which one's going off at a particular time. And timer expired really doesn't do anything except for print out the time that we've entered. It waits 3 seconds internally, and then it prints the time that we're leaving. So this just kind of gets us an idea of tracing what's going on inside of the system. And as you can imagine now, we're going to provide a butler, or in this case a thread, to run, which is our IO service, right? So service.run, that's providing the thread for the completion handler queue. And we're only going to provide one. So when we run this, we're going to get a timer event. It could have been 1, it could have been 2. But the first timer event that is done, they're both going off in 5 seconds, is going to run. That's going to come into the completion handler. It's going to run to completion, which means that it's 3 seconds before it leaves, before the next one can be serviced. Why? Because there's only one thread servicing the completion handlers. So the timer events are both done. Timers have gone off in 5 seconds. We now, on that completion queue, have 2 timer events that have completed. We have completion handlers for both of those. And now only one can be serviced at a time because we only have one thread. So let's do this with 2 threads now. So we've got the same setup, but instead of just supplying a thread, we're going to supply 2 threads. So both threads are now calling service.run. We now have 2 threads to handle the completion queue. And now when we run this, we get garbled output, right? So this completion queue looks a lot like probably Johnny. It doesn't like to have, it's not reentrant. We can't call this thing twice from 2 different threads and have safe things occur inside. So not great. How do we resolve this? Well, we could look into our toolbox of all kinds of different synchronization mechanisms that we have, and we could start pulling out maybe a mutex, or maybe some type of protected area, or it depends upon the toolbox that we have, and start solving problems that way. But this is a common problem in asynchronous systems. So there's already a mechanism to solve it. Let's just use the one that already exists. And the one that already exists is called a strand. So we've got the same setup, except that we're going to add this thing called a strand. So right here, we've got the strand. We're going to pass it the service. And now, when we go ahead and set up our completion handlers, we call async wait as we had done before. But instead of just passing the completion handler, we are going to wrap it inside of the strand. So each of these have the same strand object, and the strand object is going to take care such that only one object that's associated with the strand can actually be running at any particular time, which is exactly what we want, right? Now, the advantage of the strand is that it's not going to block other activities that might be going on. In essence, we might want to think about this as, what a strand is as another queue associated with the whole process. So that it's like a mini queue where completion events are coming in and the handlers are being queued on this small queue that's associated with the strand, and really only one of those can be processed at a time. But the overall completion queue, well, we can have another thread that goes in and grabs other things inside of that queue because they're not blocking. In fact, let's take a look at that. And as we can see, the timer does what we expect. So both timer 1 and timer 2 go off at the same time. However, only one can be running at one time, and so now they're actually serialized. Okay, so here we have a situation where we've got 3 timers. 2 of the timers, their completion handlers are wrapped in the strand, but the 3rd timer, it's not. The first 2 are going to go off in 5 seconds. This one's going to go off in 6 seconds. So what would we expect? Well, because both of these are associated with the strand, we know that they can't happen at the same time. The completion handlers cannot be running at the same time for these. However, the timers are both going to go off in 5 seconds. So they're both sitting on the completion queue. This one's going to go off in 6 seconds. So we would expect to see whichever timer completes first, that timer, its completion handler is running. And while that completion handler is running, the completion handler associated with the timer going off in 6 seconds, which is not associated with the strand, will also run. And that's what we see. So timer 1, we're in timer 1. Timer 3, we enter that. Timer 1 finally leaves. That allows timer 2 to go. So its completion handler is running. Timer 3 finally leaves, and now timer 2 finally leaves. So we want to use strands in order to help protect data. If you think about it, you have this problem all the time. If you're trying to write to a TCP socket, you really don't want multiple threads simultaneously writing to the same socket, right? That's going to create problems with your serialization, any serialization of data streams. So what do you want to do? Well, you want to write those in a strand. So you might have multiple messages coming in, but you want to contain and maintain those as a single packets. Those operations would be within a strand. One other thing we want to talk about in order to kind of pull enough things together so that we understand the examples coming up is equivalent to the owner just placing work on the completion table. And that's called posting. So there's nothing inside of the slushy shack to do. It'd be like somebody walking up and saying, hey, take this item I'm going to give you and give it to the butler. It's that same idea. There's no work to happen. It's just take it and place it on the completion queue. As soon as there is a thread that's able to take that and actually and execute it, then it will be taken off the completion queue and executed. So in a sense, this is basically a thread pool for us to use. How we do this is we use post. So we take the service, we go ahead and say post, and on that we then have the callable object. So in this case, eat, drink, and be merry. We can set this up with our thread, calling service run, and then we can eat, drink, and be merry. So the ability to just post work into the completion queue so that a thread can pick it up and run it, now we have the capability to take and potentially wrap things that are associated that cannot actually run at the same time within strands, stick them inside the completion handler, and so now we have our synchronization mechanisms handled by the strands. We can have work that just can get done as if it is some processing queue, some thread pool, as well as our asynchronous activities. All right, so with inside of the Asynchronous I/O library, we have to somehow pass in buffers and say that, hey, I'd like you to actually put the information that you're getting inside of this location. And the main way to do that is actually through what Asio calls a buffer. Buffers can, mentally you want to think about it, they're actually implemented as this too. You want to just think about them as tuples of two things, or a pair, in which the first item is a type erased pointer or a void star to the memory to fill. And the second is the size of the memory section. Now, the thing to take away from this is that it is not owned by the Asynchronous I/O library. You're simply passing a pointer and the size of the memory that you want to fill up. Or a pointer to the beginning and the size of the memory that you want to send out. But there is no ownership along the way. You still maintain ownership, which means you can't just pass a pointer, obviously, in and then have that go out of scope along the way. There are two types. There's a mutable buffer and a const buffer. And as you can imagine, mutable buffers could become const buffers, all the normal types of things that we might do. So we're going to think about mutable buffers and const buffers along the way. Asio also supports a scatter-gather. It's going to allow us to be able to store sets of buffers inside of a container and say, send these out. Or here is a container in which it has a series of buffers, and as you, buffer pointers in essence, buffers. When you read the information in, this is where I want you to store it. So scatter-gather, DMA type operations are very useful, especially if you are sending something out where you have constructed a header, you've constructed maybe the first part of the header, and then the second part of the header, then you've constructed the body, maybe you even have a tail. You might as well just stick those inside of a container and buffers pointing to each of these. And then send that out. Asio will then say, okay, well, send this buffer, then that buffer, then the next buffer. Again, buffers do not own the underlying data. When we see problems inside of client code, it's typically this problem, which is why I keep mentioning it, is that that buffer, that memory is owned by your application. And when you pass it off, you gotta take care of the lifetime of that. So how do we get one of these buffers? It's really easy. We just call buffer. And buffer is overloaded with all kinds of different things. The first example here, we are passing actually a data pointer and then the size. Here we actually have a string, and so we're just constructing an Asio buffer with the string. Here we actually have a standard array, and we're constructing with the standard array. There are a ton of overloads to this Asio buffer method that return buffers of the type that you might need. So most likely, you just kind of call it, and away you go. Let's see. This is how scatter-gather works. So in this example, we have a head, a message. We can take this head and message, and the data, and we can go ahead and create then a vector of these, and then send this. And this will take care then of sending these serialized in a serialized order. So sequentially, we'll send out each buffer the way that we would expect and we would want. All right, let's talk a little bit about a server, and we're going to put one together here. So the idea is maybe we have a chat server, or we have something where we want to communicate to multiple clients. Maybe it's a broker. So we have the server, we have these different things connecting in. As this one sends a message, that message then is relayed to all the different all the different clients that care about the information. How does this work? Well, as you know, a client that connects into a TCP listener. So something's listening on a particular port. The client connects in, and then that is handed off, right? That port is just the listening port. That's then handed off to some client handler that continues on with the communication. So the TCP listener is really only used for the initialization or the initial connection of the connection. Wow. This is now maybe the jet lag just hitting. The initial connection of the connection. And then the client handlers are going to then handle after that point. So here's the question for the day. Who owns the client handler? Where is the ownership inside of this? At which point do we decide that we need to destroy one of these? So my very first job out of college, sitting around inside of a code review, and the manager was there. The manager showed up to these code reviews all the time. It was back in the day where we did things in, printout form, and we're looking through pages and pages of stuff. And he gets to one of the pages, and it has the word manager on it, and it has a bunch of code inside of it. And he's outraged. Managers are not supposed to do anything. He got that right. All right, so I'm pretty certain he didn't mean it that way, but what we often see when we start working with clients is that this is actually a problem that's hard for a lot of people to solve. Ownership models of things often result in, I'm going to go ahead and create this client handler object. It's going to take care of communications with my clients, and I'm going to have actually a pointer to this thing or a reference on some list. And occasionally, I'm going to have a manager thread that's going to run through this and say, hey, are you still working on anything? Are you done? And if it's not, then I'm going to clean it up. All right, don't do that anymore. Because the ownership of this particular client handler is actually, the client handler owns itself, really. It knows when the work is done. When it has nothing else to do, when there's nothing left to write to the client, or there's nothing left to read from the client, it doesn't need to exist anymore. When the client disconnects, there's nothing else to do, right? It should just go away. It can actually manage its own lifetime. So we want to talk about how to deal with that. And this is actually a pattern that you'll see over and over again when you use Asio. And the basics of the pattern look like this. At some point, we're going to have something like QAsync read. And we're going to pass to that QAsync read a completion handler, read done. So it's doing some reading in the background. That's inside of that slushy shack. And then when it's completed, onto the completion handler queue, it's going to get stuck this read done. And read done is going to get called in when all the data's there. Read done will do what? Well, the first thing it's going to do is say, do I have an error or do I not have an error? If I have an error, something bad happened, let's just exit. Let's just leave. Don't do anything. But if I don't, I'm reading, right? I probably want to queue another read. So there's no error. I've got more work to do. I'm going to queue another read. And so we see this cycle in which we're queuing another read. There's always another read done stuck. We're going to use that for our advantage here in a minute. So we have a server. Client's going to connect into this Asio generic server, because really, servers are very generic, right? They just listen to a port, and eventually they're going to hand their work off to, in this case, the chat handler. It's going to be handed off to that. So eventually, the client is really talking here to the chat handler object. We add another client. We basically get another chat handler object. All right, so we're going to create an Asio generic server, and it is going to be parameterized, a template parameter, of actually the handler object that we want to deal with. It's called chat handler. We have this server, and we're going to start the server, and we're going to pass it the port that we want to listen to. What's inside of these? So the generic server, first thing we have is this type that we're going to alias, and it's a shared pointer to whatever the connection handler is. In our example, it's going to be the chat handler, but we have a shared pointer to that. So we're just going to call that our shared handler type. We're going to store a thread count. We can have multiple threads that are dealing with this. A vector is going to represent our thread pool in this case, so that we can take care of that a little bit later. And then we'll have our I/O service. And for the TCP, on the listening side, we need an acceptor. The constructor, we're going to initialize these things. We're going to have a start server method, and then we're going to have a handle new connection method. The handle new connection method is going to take two parameters. It's going to take the handler itself. This is like the chat handler. And it's going to take the error code. So what does start server look like? Well, start server, we're going to make shared a connection handler. So we're going to create a shared pointer to whatever the connection handler type is, and we're going to pass it the I/O service. That's going to be our handler. We're going to set up the listen. So listening requires us to set up an endpoint, open that up. We can set some options. We're going to set reuse address to true. There's a whole series of options that we can set. We're going to bind to the endpoint, and then we're going to start the listen. And then we're going to call accept. And we're going to call accept asynchronously. So by calling it asynchronously, we're saying, hey, when you actually receive something in on that listen, when you accept a new connection, this is the callback handler that I want you to call. We're providing it the socket, and we want to call the completion handler, which is handle new connection, passing it the handler, and the error code. So remember, handler is this the client handler in our case, so the thing that's going to handle the actual connection itself. Notice it owns the socket. So the listener is just utilizing the socket for us. And then we're going to go start our thread pool by calling IO service run on the variety of different threads that might have been passed in, so however many threads there were. What does handle new connection do? All right, so super easy. If there's an error, it's going to return. We're just going to like not do anything for now. You guys can add your own error handling. And then we're going to call on the handler whatever its start method's going to do. We're going to call start. So that's going to get things going for the handler. At this point, remember, the handler now has a connection that has come in. There's a new client. We're going to create a new handler and start the whole process off again of calling async accept with the new handler, and we're going to handle new connection. All right, so a client coming in, it gets a new connection. We're just going to hand that off to the handler. It's going to take care of the connections, because that's what the connection handler does, and we're just going to start accepting a new one. All right, so what is this chat handler? The chat handler has a reference to the original service. It has the socket, the real socket. It has a strand to deal with writes, because we can't write from multiple threads to the TCP socket. That would be disaster. We're going to use actually a stream buff for the in packet. Notice before we were using just buffers. There is inside of Asio a stream buffer, which looks more like a stream, and we're going to go ahead and utilize that. And then for our outgoing, we're going to use a deck of strings, just because. Going to initialize one of these, and socket was what we were using as the interface inside of the generic server side, and that simply just returns the socket so it can be utilized. And then what does start do? Well, it calls read packet, because that's how we're going to start doing all of our operations, is we're just going to start reading. And as long as there's an outstanding read to do, we're going to consider things okay. So what does read packet look like? We're going to use a read until method, and the Asio read until, we pass the thing that we want to read from, where we want to place the stream of information that's being read, some terminator or condition, or this can be a complicated predicate. There's all kinds of different things we can do here. Here we're just going to look for a null. And then the completion handler itself. And the completion handler, here's part of the trick. What I'm doing is I am assigning shared from this to me. Now, our chat handler, it inherited from enabled shared from this, which allows me to call shared from this and get a shared pointer, the shared pointer to that object. So now I have the shared pointer to that object bound to this me member that is part of the closure object, which means that the closure object itself, as long as it's alive, I have a reference count to that object. And what's going to happen to this thing? Well, it's the completion object. It's going to get stored inside of the IO service. And it's going to hang out throughout the call to the completion handler, right? It's going to continue to exist, which is going to allow the lifetime of this object to be maintained. Internally, what I'm going to do, I'm just going to call read packet done and pass it the error code and the bytes transferred. What does read packet done do? If there's an error, we're not going to really do much. We're not going to worry about error handling, but we're going to return right away. Well, why are we going to return? Because otherwise, in this case, we're going to do stream processing of some sort, and then we're going to call read packet again. Well, what does read packet again do? It goes ahead and takes a shared from this, sticks it inside the queue. At this point here, because we return, we're basically not queuing a reference to ourselves back into the completion handler or back into the IO service. As a result, we're going to fall off the stack eventually, right? Our reference count is going to go 0 once there's no more work to do. How about on the right side? When we send, we're going to actually post our sends with a strand. We're going to wrap that, and we're just going to call our own queue message. So writing is we're going to queue a message. Queue message does nothing more than checks to see whether or not the queue is empty or not. If it's not empty, then there must be a write in progress. We're going to push back the message, we're going to, if there was not a write already in progress, we're going to start the packet send. Now, this is normally a bad thing to do, right? Multiple threads talking and trying to figure out what to do with standard containers. But we've actually wrapped this inside of the strand, and as a result, we know that there's only one thread that can possibly be handling and dealing with this at a time. Why? Because the send itself is also wrapped in a strand. So here's our send. We're going to take the packet queue's front, add on packet queue front is the next message to send out. We're going to send a null terminator onto the back of that. We're going to asynchronous write to the socket, providing it a buffer with basically queue front. This is our string, which is going to get us our buffer. And we're going to wrap this into the strand, again, using this technique of taking shared from this, that gets us our reference. So we're going to extend our lifetime as long as this is alive. And the completion handler is going to call packet send done. Packet send done, if there's not an error, well, then at this point, pop the front. We didn't want to pop the front before. We can now pop the front because we can now get rid of that memory. And if the queue is not empty, well, we want to start sending whatever the next thing is on the queue. All right. So this was a very simple example. Asio has a lot of features in it. But the basics of what you just learned are the basics that keep you out of trouble. Lifetime management for these completion handlers is best done by dealing with taking a shared pointer and queuing it, somehow taking that shared pointer that's going to keep you alive and sticking it inside of your closure object that's going to get queued up. It might not even be active. You might never even use it, but you need it bound in there. The other thing you want to do with Asio is you don't want to actually handle all of your work inside of those threads. You want to use some layered approach. And so this is the most common way to do it. You have some Asio service that maybe has one thread, because you only need one thread for your communications. That's it. And you have another Asio service that is basically where the processing is going to occur. So as messages are received in, that initial processing of the message, so it's like some packetization of some sort, you have a message, you take that message, and then you pass it off into another Asio service. And you're really just using this as a thread pool. You may have another type of a thread pool already in your system. If you don't have a thread pool already in your system and you need to decouple those, just use an Asio IO service and post. That's one way to do that. All right, so you want to use layered designs. You can use it as a processing queue. You can add all of your own services to do a whole variety of different things, communicate to really anything asynchronous that's going on in your system. You can add a new service to deal with the asynchronous things and always stay inside of Asio in that environment. And a lot of the things that we do internally within our company is we actually combine Asio with MSM, which is the meta state machine, and Spirit. So we will have Spirit taking data structures. So we actually queue data structures, which then go through Karma and become a stream of bits going out. And as those stream of bits are coming in, it goes through Spirit, which on the other side of Spirit transforms that into the struct that we wanted, the data representation that we wanted. And those are getting placed back onto queues. How do we deal with all these crazy completion handlers all over the place? Chaining completion handlers is horrible. There are a lot of different ways to deal with this. Some people really love coroutines. I actually like state machines. So what we do is we deal with this through state machines. As new events are coming in, those are actually going into a state machine that then is processing the higher level states of where we are and what we need to do next. So those are really good tools, those three things to combine. These are also Boost libraries. All right, and that is the brief of Asio. I think we've got, maybe do we have time for questions? I have actually no idea what time it is because my clock is now missing. All right, so we can take a few questions. All right. right, we can take no questions too. Oh, there's one right here.
Wait.
Yeah, we tried to do something similar, but we had problems with the shared pointers on the I/O queue, which might keep our objects alive too long. So we end up with putting weak pointers on the I/O queue and then locking them when we needed to call the callback. But we found all this quite difficult, and we thought whether this is actually really the simplest way to do things, because we found it quite vulnerable to programming errors, like people forgetting to do something, to people sending shared pointers on the queue, and then it could keep our objects alive forever when the user expected the objects to be deleted, and this had effect on the user when we called callbacks from objects the user thought were already deleted, and so on. So I don't know whether this is actually...
So dealing with this idiom for programming can be actually complicated the first time that you do it. So a couple things to keep in mind. So one problem with a weak pointer is weak pointer does not extend lifetime, right? So that's the whole idea of the weak pointer. It has no ownership or share in the ownership. And so what can happen by queuing weak pointers instead is the fact that now, because there is no ownership, whatever has the shared pointer might go out of scope, yet on the completion queue is still the handler that needs to be called at some point. If you cancel all the I/O that's going to be occurring, those completion handlers get called with errors. And so the completion handler is still going to get called, and the object may no longer be in scope, even though you had a weak pointer, right? You can't just get the weak pointer and lock it, because what are you going to lock? So it's possible, if you've wrapped it inside of closure objects or lambdas, to check to make sure not to do that. Is that what you did? Yes. Yeah, okay. So you can definitely do that. The trick works out to be dealing with each small section at a time and not trying to think too large about the problem. So if you narrow it down to what does the lifetime mean for each bit and part, like on reads, what does it mean as I'm reading to have ownership in being able to extend my lifetime? If I read and I have an error, I don't need to queue anything anymore, right? So if I'm reading something and I have an error, then I don't need to queue anything. If I'm writing and I have an error, I don't need to queue anything. If I have read something and I have an error, I don't need to write anything, or excuse me, I don't need to read anymore, but I still have write completions on the queue. I need to have those stay alive and deal with that in some manner. So what happens a lot is what happens when the client terminates, right? So you've got the client coming in, the client has decided, like, maybe there's a clean way for the client to go away, or maybe even not a clean way for the client to go away, but the client has gone away, and now your reads are no longer good, but you have these writes that are still hanging out. And so sometimes that can be what extends your lifetime, and in that case, what you want to do is you know from your application point of view that what you want to do is have that client actually go away. And you can then cancel all of the I/O that was queued up for that client, cancel that I/O, and then have it fall off properly, and then the object will be destroyed. So I think it's just like taking great care in what you queue and when you queue it and how you handle those errors. You should not have a problem. Though you clearly did. I would like to talk more to you, actually, to find out more about maybe what was causing your lifetime to extend. Are there other questions? Yeah.
Could you elaborate more about the spirit approach? Can you? I'm not sure I get your point. Are you using spirit for data serialization, deserialization?
Yeah. So the question is, how do you integrate spirit into this? What is the idea? So if you think about I/O as just being a stream of bits across anything, right? You have you have data structures that you're naturally dealing with, and you need to serialize those somehow. Or you have a serial stream coming in, and you need to bring those in and create data structures out of it. What we do, and we could use like the read as an example. So you're reading a stream coming in, and actually this is the place where coroutines work really well. So you have a stream of data coming in, and as you read basically what is currently available for ASIO at any particular time. Whatever happens to be inside of the read buffer. If it has any data at all, you read that in, and you're bringing that into a stream. So that's part of the coroutine. It takes care of hanging out and waiting for more data to come in. And while it's not doing that, it's using Spirit to do the parsing, which is taking this stream as the data comes in, and it converts it then into some object. And once the object is done, like out of Spirit, you're going to get from a stream of data, you're going to get like real objects out, right? Or a variant of objects out. You take that object, or that variant type, and now you've got one. It came in, and you just queue that somewhere to have it processed and to be worked on. The other way, the opposite way, is you take the object, and you're queuing those objects instead of actually queuing strings. You queue the objects, and then you serialize them out using, in particular, karma. And this problem could be abstracted to the point where it's very, very generic. What we do is we actually supply, this is what the grammar looks like for reading, and this is what the grammar looks like for writing. So our abstraction basically is we pass in two grammars, and we just send objects, and we just receive objects. So it's actually a really nice abstraction. Are there examples? I'll give you my business card, and you send me an email, and I will give you examples. How's that? Yeah, we can open source this. It's not a problem. Yeah, the question is, do you see an advantage of using Spirit instead of protobuf? We don't use protobuf a lot. We use Spirit a lot, partially because, so Joel de Guzman, who's the author of Spirit and Fusion, Phoenix, works also with Kira, so we maintain Spirit. We're doing this all the time. We find that Spirit does exactly what we need for conversions to all kinds of weird types along the way. So you can imagine, I've got data structures that I'm trying to speak on a CAN bus with. That's a very particular thing, not a protobuf thing, right? So protobuf is fine if you've got protobuf on both sides, and you're communicating protobuf type stuff, or you translate that into something else. But if you're already translating, you might as well just write a Spirit grammar that tells you how to take data structures and translate them into the stream that you already want.
You're talking TCP/IP. Is there a high-level abstraction API for starting porting legacy code?
I'm sorry, I didn't catch the last part. Is there a
code? Have you any recommendation for some high-level APIs?
Yeah, so good question. So no, ASIO is actually low-level, dealing with asynchronous I/O. There are a variety of different libraries that people have written on top of that in order to deal with higher-level concepts. There's one that's going into for Boost review, hopefully next month, called Beast, and Beast deals with now I just forgot. That's really bad since I'm the review manager. Oh, what's that called? Something sockets with all of those web guys. WebSockets, of course. Wow. Bing. I'm under-caffeinated. So it deals like with WebSockets and other HTTP type things. There are a lot of people who've written things like that. Dean Michael Barris has a library that's also very similar, where it deals with all kinds of web type communications, email and stuff. It's all written on top of the asynchronous I/O library. So you can think of this as like a lower level that you might put protocols and things like that on top of. It's a good question, thank you. Anything else? All right, thank you very much for your attention, and I'll be around.